Markut UAV team is a multidisciplinary team of successful students who have achieved in various national and international competitions. Our team consists of 9 engineering students and 3 separate sub-teams. Mechanical team consists of 2 mechanical engineering students and 3 aerospace engineering students, in total 5 members. Avionics team consists of 1 electrical and electronics engineering student and 1 industrial engineering student, totaling 2 members. Software team. Our software team consists of 2 members studying computer engineering. The 5 headings of the specification were examined in detail, and the analyzed competition requirements are shown in the table. Teams must complete a true autonomous cargo drop mission within 30 minutes without pilot intervention. Each team must drop 5 loads on alphanumeric targets at a minimum distance of 75 feet. The targets must be detected using image processing software. The drone must follow GPS locations to a maximum of 3 miles before airdrop. It must then locate the desired alphanumeric target. The same process is repeated 5 times with different targets. The goal is to complete all tasks in the shortest time possible, using previous experience with drones and artificial intelligence.
System overview. Our mechanical team has designed a modular design considering durability, stability, and optimal mission duration. After motor and performance calculations, a flight speed of 20.5 meters and a flight time of 37 minutes have been determined. At the end of the mission, 25% of the battery will remain for safety reasons. The main body consists of a monocoque chassis and 2 glass fiber plates. Taking into account the flight time and mission requirements, an appropriate motor has been selected. Based on the selected motor data, a 22-inch carbon fiber propeller has been chosen for optimum performance. Our chosen motor is powered by a specially manufactured 6S10P Lion battery with a capacity of 42,000 mAh. All our missions are processed autonomously on board in the computing unit. For this purpose, we use a Cube Orange based on PX4 and accompanied by an NVIDIA Jetson Xavier NX computer. Our communication infrastructure is provided by RF and Wi-Fi based protocols. On the screen, you can see a Ubiquiti brand Bullet M5 device. It provides both image transmission and telemetry transmission when needed. An 868 MHz telemetry device is chosen for telemetry. For collision avoidance during autonomous missions, escape photography positioning are critical for the successful completion of the mission. A Raspberry Pi HQ camera is used to capture sufficient images from 75 ft altitude. To dampen any possible vibrations of the camera, an appropriate gimbal is used. The mission mechanism system is designed uniquely using 5 DC motors to release 5 water bottles according to the body geometry. After our UAV is ready for flight, the ground control station operator will transmit location and target data to the flight computer on the UAV. Upon receiving location data, the UAV will ascend to 75 ft altitude and, upon reaching the scanning area, will use image processing to detect the given shapes and safely deploy the payloads using the mission mechanism. This process will be repeated 5 times. After completing its missions, the drone will return to the takeoff point.
First, images were created for all possible combinations of shapes and letters. These images were then resized to dimensions visible from 75 feet to match the background images resembling the competition area's floor. This dataset was used to train the road detection model. The size of the image from the camera has been reduced to reduce the processing cost of YOLO. The shape detected by YOLO is cropped and the color is detected using OpenCV. The object with the detected shape is cropped from the original image, and the alphanumeric character is identified using CNN. After color detection of the identified image, its location is determined by localization along with the shape position and then recorded. The contest concept was tested in the simulation using Gazebo and PX4. Images were generated and placed in the simulation to test ODLC. As a result of these tests, our object recognition algorithms and autonomy parts were improved. As a result of these developments, it is expected that the entire mission will be completed autonomously. The goal was to select the most accurate camera and lens combination, so the tests were based on specific distances. The average pixel counts of the shapes and letters in the images taken from 75, 80, and 85 feet are shown in the table. First, images were created for all possible combinations of shapes and letters. These images were then resized to dimensions visible from 25 meters to match the background images resembling the competition area's floor. This dataset was used to train the road detection model.
The payload release mechanism consists of a light and simple mechanism suitable for the body dimensions. Due to its ease of use, the mechanism is produced from PLA material with additive manufacturing methods and consists of many subparts. A 5-compartment plate is designed for 5 bottles. Thanks to the plate, the bottles will not touch each other during the flight, and possible shocks will be prevented. Each bottle will be controlled by their DC motors. The DC motor will control the ropes with a gear mechanism. Since speed is important during the task, a Novamax DC motor with 400 RPM, 14.33 pound per second, and 25 operating voltage was preferred. Holding mechanism has been designed to easily separate the bottles from the system after they come into contact with the ground during the load release process. Thanks to the mutual magnets placed in the mechanism, when the bottle touches the ground, the magnets will stick to each other and release the bottle safely. The mechanism holds the bottles without hassle, even in case of possible shaking. When we reach the bottle dropping area, after the messages sent from the Jetson reach the Arduino, the bottles will be bring down through the DC motors controlled by the Arduino outputs. In order to prevent falling and shattering when descending from above, the mechanism that holds the bottles will open after they touch the ground.
The wireless communication system consists of 2 data links and an RC controller. The RC controller is used for manual control and security, while the redundant data link system is used to transmit telemetry data and control commands between the UAV and the ground station. In total, 3 different frequency bands are used to prevent interference between the modules. The communication subsystem is divided into 2 parts, the UAV and the ground station. The Bullet AC model on the UAV operates in the 5.8 GHz band and provides high-speed video and telemetry data transmission over UDP/TCP. The RFD 900X model is used for autopilot control from the ground station and backup telemetry data link using the Mavlink protocol. Operating in the 900 MHz band, the module provides protection against frequency interference using FHSS technology. Offering a communication range of 40 km in open air, the module provides a data transfer rate of approximately 200 kbps. The RC receiver in the system operates in the 2.4 GHz band and provides manual control of the system. Using the ELRS protocol for communication, the RC receiver can transmit packets at 250 Hz over a distance of 5 km in open air. iPerf tests have shown a data transfer rate of approximately 20 megabits per second at a range of 5 km. Statistics such as number of autonomous flights, average amount of time spent in manual mode per flight, number of waypoints attempted, the number of waypoints hit, and the average waypoint miss error should be clearly presented.
Aircraft design and testing. General design. Tasks and requirements were evaluated using sensitivity analysis methods. It has been determined that rotary wing aircraft provide satisfactory results in terms of maneuverability and hovering abilities. It is planned to benefit from the ability of rotary wing aircraft to hover in the air, fly at low speeds and navigate in narrow spaces during the load-drop process. Quadcopter configuration as a rotary wing configuration has been preferred due to its simplicity, lightness and agility. Weight. During the design phase, the weight of all parts was calculated as 9.6 kilograms. After the production method, the piece was measured to ensure accurate weight planning, and its weight was determined to be 9.5 kilograms. Dimensions. Our Markut UAV vehicle, Designed modular, has a height of 200 mm and a body measuring 280*180 mm. The distance between the cross arms is approximately 991 mm. The diameter of the carbon fiber pipe is 25 mm and the length is 850 mm. Taking into account flight mechanics calculations, carbon fiber arms were integrated into the body at a 5-degree angle. Design. The body, which contains critical electronic components in terms of lightness and durability, is designed from 2 mm aluminum material in a rectangular form and integrated into the 7000 series aluminum landing gear. A carbon fiber plate is used to integrate the battery into the body and cover the lower body. A cover made of PLA material was designed on the drone. Taking into account flight mechanics calculations, carbon fiber arms were integrated into the body at a 5-degree angle.
A cover made of PLA material has been designed for the drone. The body housing the electronic components is designed as a rectangle made of 0.12-inch thick aluminum material.
Analysis. Engine and flight performance analysis. T-Motor U7 model engine was preferred, taking into account aerodynamic and flight mechanics calculations, the forces that will arise during flight. Flight duration and mission requirements. T-Motor CF 22-inch propeller was chosen considering the selected engine and body dimensions. Engines and other avionics will be powered by a Li-ion 40-1000 mAh battery.
After engine and performance calculations were made, the flight speed was determined as 29.82 meters per second and the flight duration was determined as 30.2 minutes. It is calculated that 25% battery will remain at the end of the mission for safety reasons. Maximum speed during flight is calculated as 29.82 km per hour. 1.7 thrust-weight ratio is obtained for 857 watts of power. In the analyses, the deformations and stress concentrations of the vehicle in two different states, the takeoff moment and the hover moment, were examined. In the data obtained, the amount of stretching in the arms at the time of takeoff was measured to be approximately 0.059-inch maximum. The stress concentration was taken as 9 MPa in the part where the arms are connected to the body at the time of takeoff. Flow analysis. The CFD simulations of your vehicle demonstrate an aerodynamically efficient design capable of effectively managing airflow. Observed turbulence indicates that the vehicle can maintain stability even in complex atmospheric conditions, ensuring a safe and controlled flight experience. Detailed analysis through 198 iterations suggests thorough preparation for various scenarios. This underscores the vehicle's potential for strong performance in competitive conditions. Manufacturing. The chassis designed for the body was cut from 3 mm aluminum sheet metal with the help of a laser machine and then bent using a bending machine. The bent aluminum chassis parts were welded using aluminum welding. Glass fiber plates have been cut under and above the chassis in accordance with the chassis. The cover piece was produced with the help of a 3D printer to cover the drone. The legs, designed from aluminum material, were cut using a laser cutting machine. The parts welded together are integrated into the body with the help of carbon pipes. Markut, who stayed in the air for more than 6 hours in total, made 21 flights. The previously calculated values such as maximum speed and thrust were confirmed by the log records obtained from the flights. The PX4 autopilot software and Cube Orange flight controller module are chosen for the drone's autonomous flight. The Cube Orange flight controller module houses sensors like IMU, barometer, and compass, which are essential for autonomous flight. The autopilot offers a safe and high-performance flight thanks to its redundant sensors and high processing power. The PX4 autopilot software is preferred due to its autonomous flight support and strong ROS2 communication interface. Controlling the drone's autonomous flight, the PX4 software communicates with the ODLC and software running on the Jetson via ROS2. PX4 software sends position and velocity data to the ROS2 system, which in turn transmits set points to guide the drone's autonomous flight. A detailed tuning process is performed to ensure the successful execution of these set points. The drone's step response and vibration graphs are analyzed, and the controller coefficients and filters are adjusted based on the log data. New coefficients are then verified through extensive test flights. Statistics such as number of autonomous flights, average amount of time spent in manual mode per flight, number of waypoints attempted, the number of waypoints hit, and the average waypoint miss error should be clearly presented.
To fully satisfy the autonomy feature that is one of the objectives of these missions, we have integrated obstacle avoidance algorithms into our UAV. The obstacles detected by the vehicle's 360-degree radar are fed to a 3DVFH plus-based algorithm, enabling it to follow the path without deviating from the intended target.
Choosing alternative configurations was another approach to performing UAV tasks in the most appropriate and efficient manner. We evaluated various types of aircraft such as fixed-wing, quadcopter, and hexacopter. Fixed-wing of UAVs are not suitable, especially in situations where precise payload release from a specific altitude is required. Therefore, multirotor drones, which offer greater maneuverability and precise control, are generally preferred. The fixed-wing UAV option was eliminated based on our previous experiences due to its disadvantages such as low maneuverability and long turnaround times, although having a high payload capacity. Therefore, when precise and controlled payload release is necessary, multirotor drones may be a more suitable option compared to fixed-wing drones. Our team's other design choices were hexacopter and quadcopter. Factors such as propulsion, efficiency calculations, and ease of manufacture have inclined us towards the quadcopter configuration. The X-frame offers advantages such as increased maneuverability, reduced air resistance, and a wider field of view. Therefore, the X-frame was preferred. We compared the technical specifications of Orange Cube, such as processor speed and memory capacity, and found that it offers more powerful hardware. These data indicate that Orange Cube is more suitable for processing complex tasks and algorithms.
These are our development tables, and these are the mitigations. In this project, you can see the autonomous cargo drone developed and produced by our team, which will compete in SUAS next June. We believe that the drone developed for this purpose can fulfill its purpose and autonomy tasks properly. Thanks to our team and sponsors